Okay, problem number 4 on the Geogebra review. Let's check to see if this point C right here is on the perpendicular bisector of the segment AB. Why or why not? Okay, so from our perpendicular bisector theorem, we should know by now that any point that is the same distance from the endpoints is going to be on the perpendicular bisector. So we could check that way. I'll show you a couple ways here. So I could do like a segment to show the relationship between C and A and C and B. And just kind of looking at it, it looks a little off to me. So I don't think it is on the perpendicular bisector. We can check the distance by grabbing in our measurement toolbox here, grabbing that length tool and just clicking on the segment. And not the same length. So no, C is not on the perpendicular bisector because it's not equidistant to endpoints A and B, so it's not on there. Okay, also we could have grabbed our perpendicular bisector tool and just clicked on the segment, and we can see that it's not on there also. And watch as I put C, well actually I can't move C, but watch as I put a point on the perpendicular bisector. That's isosceles, right? That triangle that's formed. It's going to be isosceles. And those distances are going to be the same, right? So be able to just understand equidistant point. Equidistant to the endpoints is going to be on that perpendicular bisector. If not, it's not on the perpendicular bisector. Okay, problem number 5. Find the center of rotation. So we have a rotation here. Okay, it's not a reflection because we can see that C and C prime, B, B prime, they're on different sides of each other. Okay, so this is a rotation, so we need to find the center of rotation and the angle of rotation with direction. Okay, so I'm going to grab my segment tool. I'm going to connect a pair of pre-image and image points, maybe B and B prime, and we'll go C and C prime. I'm going to find those perpendicular bisectors, so I'm going to just grab that tool of these segments. So there's our center at that intersection, right? So we know that this, looking at A, B, C, D, right? We have A prime, B prime, C prime, D prime. So this was the pre-image. It rotated around this point F, some angle to rotate to this shape. Okay, so it rotated clockwise. There's our direction, so it's going to be a negative angle. And we can measure that angle. So all I really have to do is, and I'll just show it, use my ray tool. It's in our line toolbox. Draw a ray from our center through one of the points, maybe like A prime. I'll make that stand out a little bit. F to A. Okay, so there's our angle. So to measure it, I'm going to go in a clockwise direction. A prime, vertex is always the second point, and then A, and it looks like it was an angle of 95 degrees clockwise. So that would be our answer. Find the center right here, angle of rotation 95 degrees clockwise. Okay, problem number, what is this, 6? Construct a regular heptagon with the given segment as a radius. Okay, so one of these points can be the center. The other point will be the point on a circle, right? That's what radius means. So I'm just going to grab my circle tool, and maybe A will be the center. And B, I'm going to click right on B. B will be the point on the circle. So now we can see that that's going to be a radius. We just need to rotate B now, some angle to make a heptagon. So hepta means 7 sides. So we have to take 360 degrees, a full revolution, and divide by 7. And let's see what that is. Doesn't seem like it's going to be a whole number. 360 divided by 7. 51.4285. Ooh, man, that's going to be hard to get exact. Let's go 51.43. We're on to the 100th. So about 51.43 degrees. Okay, so now I'm just going to grab my rotate tool. It's in the transformation toolbox. We're going to rotate. I'm going to rotate B. Rotate B around A. And I'm just going to actually try to go 360 divided by 7. I think that'll give us the exact angle. Hey, check that out. Okay, so I'm going to take B prime and rotate it around A, same angle, and just go around the horn. Oops. If you mess up on your points, just hit escape on your keyboard, and then just grab your rotate tool again, and just continue what you were doing. Okay, I'm not going to finish here because I'm going to show you something too. That's the rotation method of how we can construct any regular polygon. Just take 360 divided by the number of sides, because for each side of the polygon there's an angle formed. So the angles and sides are what we say 1 to 1. For every side there's an angle. So it's easier to think about polygons as sides, number of sides instead of number of angles. So that's why we take 360 and divide by the number of sides. That'll tell us how far to rotate each point to make our shape. Geogebra has this polygon toolbox, and I showed you a little bit in an earlier video using the regular polygon. Direction matters in the way that we click, but we're gonna click on 2 points that are gonna make like the side of our regular heptagon. So it'd be kind of like this. I'm gonna grab my segment tool. This is like a side, right, of our heptagon. So I'm going to grab my regular polygon tool, and I'm going to click on one point and then the other point. So I'm measuring to GeoGebra. This is the side length. How many vertices do we want? It's a heptagon, so we want 7. And click OK, and check that out. There's our regular heptagon, and there's our vertices, and it even continued for us and made that. So the interior shaded, that means that we used the polygon tool, so we could actually measure area, circumference. We could do all sorts of good stuff. We can transform this whole shape as a polygon. But anyways, in GeoGebra, that's how we use the polygon tool. Okay, last one for this video, question number 7. A student thinks he can make a regular polygon by rotating the vertices 50 degrees. Is he right? So if we rotate 50 degrees, is this going to evenly rotate our points around to make a 360 degree rotation with points, right? With the rotated angle being 50 degrees. Let's check it out. I'm going to do a circle, put a point on it, right? I'm going to grab my rotate tool. We don't need the radius. I can rotate B around A. Oops. Try that again. B around A, 50 degrees. Okay. B prime to A. And we can just try to continue this around, see what happens. So that would be like 100 degrees, 150 degrees, 200 degrees, 250 degrees, 350 degrees. 350 degrees, well, we would only have, 10 more degrees to go to get to 360. That's not an even, amount that we can rotate, right? So notice we have this extra 10 degrees in here. Okay, so that's not going to make any polygon. So that not a regular one. I hope that makes sense. We don't have an equal number of 50 degree rotations that equal 360 exactly. We have a remainder here. So not a regular polygon. We could have also checked if we took some number. Let's see here. What number, if we use our little formula, I'm going to grab my pen tool, 360 degrees divided by, we're trying to find the side length, right? If this is going to make a regular polygon, we would divide by the number of sides. That has to equal our angle of rotation, in this case 50 degrees, right? So what number do we divide 360 degrees by to make 50? Well, another way of thinking about this is 50 times n, right? If we multiply these two numbers together, doesn't that have to equal 360? And if we think about it that way, then I can divide both sides by 50 now, and that would tell us the number of sides. So this equals n, right? If we take 360 divided by 5, that would tell us, or excuse me, divided by 50, that would tell us the number of sides. And if it's a whole number, then this would be a regular polygon, right? Because n would have to be a whole number of sides. So if we take 360 divided by 50, 7.2. So notice we have that 0.2 sides. That's that extra 10 degrees right here, right? So the algebra is another way that we could use to argue if it's going to make a polygon or not. So in this case, no, the student would be incorrect.